Okay, so let's start with that first question. All right. So here's what you're trying to depict is that here's this loop. And if you look at how this is defined, you have your x, y, and z axis. So the y-axis is what you want to spin about. So with that said, if you look on this arrow here, all right, you want this to spin in this direction, but the current's going in this direction. Okay, so if you're looking at this wire, I want this side to spin up, but the current's going this way. So I want this side to spin up, and I want this side to spin down. Okay? Cool with that. So, because the current's going in this direction, so I'm going to go over here, I'm going to start on this side over here. So if the current's going in this direction, right, and I want this side to spin up, that means this side has to spin down. So the current's going this way, but what do I want to have happen in terms of this force? I want it to, no, because I want this side to go down. So the current's going like this, but I want this to go down. So the only way that can happen is if the magnetic field is going in. That's how you can figure out that direction. Okay, hey, the current's going this way. I want that to go down. Which direction is my finger going to point? Now, here's how you can verify it. Go to the other side, okay, where that current is coming down this way. And I want this side over here to go up. So if I take this figure, and because it's going to be going this way, and I want my fingers to point, in this case, upward, so that's going to go like that. I want that to go up. Both sides should have the magnetic field going in the same direction. Okay? I can't have one wire having a magnetic field going in one direction and the other side of the wire having the magnetic field going in the other direction. So that has to be the same.
Hey, you're in the camera.
A lot in the camera. So on question number 3, okay? So if that's wrong, everything is going to be wrong. So what do you have as your answer to number 3?
Plus x.
Plus x, moving to the right, however you want to put it.
Let's go.
Okay? All right? Now, when you get to question number 4, I said, does it make any difference which side of the square in the y-plane is chosen to determine the direction of the field? Okay? Yes.
So when you say the y plane, do you mean like these two or these two?
No, I'm talking about by making it spin, by talking about this y-plane like this.
So the two sides that are parallel to the axis of rotation.
Yes.
Well, look who's right.
That wasn't my argument.
Yeah,
I wasn't confused on that.
Then what was your argument, Chad?
I didn't know that.
It wasn't that.
I
It was
thought he was meaning like what of the sides.
Well, magnetic field of the y-plane creates needed torque. Okay. So what I'm talking about here, so what I'm saying is that in the direction of the current, if I send the magnetic field, it doesn't make any difference, just in the y-plane, either this way or this way. So if I want it to spin like this, if I put it in a magnetic field in this direction, the magnetic field goes this way. Can I make it spin like this? Yeah, so if I did that, the current would be going parallel with the magnetic field.
No force. Nothing happened.
And there's no force.
And the ones that do feel force are bound by the axle.
Yes.
Okay.
Yeah.
The ones that
On number 5, which was a doozy. So the first thing you have to figure out is the mass of the wire. Okay? which is, and you know the density is mass divided by volume, so if you can find the volume, you can find the mass. Okay? So the total mass should be around 0.2 kilograms. Okay? Total mass should be around 0.2 kilograms. Now, because of the fact that you're making this thing spin, that means you have to apply a torque to it. And torque equals two things. Force times radius, I fish. Now, the torque, right? Okay? So, to get the torque, that requires that you have a force, right? But to calculate the force, it means you have a current moving in a magnetic field. So the torque is going to be force times radius, but the force is going to be built. Okay? Because you know the magnetic field strength, you know the current. Now, the length of this is whatever is actually in the magnetic field. Okay? It isn't the entire length, it's whatever is going to be fueling that particular value. So, when you get done, one of the things you need to find is the value of your angular acceleration. That would make a decent GPA. Okay? Decent GPA. And your overall final angular velocity after 2 seconds should be between 5 and 10 radians per second.
Because it's 6.7.
Spoiler, bro.
I'm just saying it's between 5 and 10.
That's what you said for now.
Whatever, however you want to play that out.
You actually need to work to give you a
Oh, your answer to number 6 for that second current should be between 12 and 20.
For 6.
Okay?
That's what it is in my
Now, when you get to number 7, the circular coil of wire has a diameter of 20 centimeters, contains 10 hoops. Now that you have the current is placed in a 2 Tesla external magnetic field. So, technically that torque is NIA B sine theta. So, here's where this plays out. So, you have a thin hoop, okay, has a certain number of loops. You're going to put it in a magnetic field, right? So, what this is going to give you, and if you think about it, this should make sense. So, the area, right? As the area gets bigger, you're going to have more area exposed to the magnetic field. That's going to create more torque. The more current that you have means you have more particles interacting with it. Oh, that's going to make it bigger. N is the number of loops. Okay? Okay? Now, so here's what you want to think through. It says determine the minimum and maximum torque. So that needs to be based upon the idea that if you have that current going around in that loop, if the magnetic field is running parallel with the loops, how much force and then how much subsequent torque would there be?
None.
None, because they would be running parallel with it. Okay? So your minimum torque is just what? Zero. Okay? That's just going to be 0. So when are you going to have your maximum torque?
Sine of 90.
Yeah, when it's at right angles.
something more than one.
Something more than 1. Yeah, your answer to number 7 on that max torque would make a not so good GPA. Really bad.
Okay.
Like Gavin.
Gavin has a 3.8.
Wire.
Unweighted.
Listen.
Weighted is 1.2.
Kevin has a 3.8.
Gavin is way above average.
On, let's talk about number 8.
And you're fine.
You guys are way above average, okay?
Is this a better GPA?
What do you get?
Wait, it's better?
No.
I did not get that. Uh-oh.
Yeah.
Well, you're gonna explain it. Oh, yeah.
I would rather have this than this. Wait.
That's like
What is a
squeeze.
square? What is a square?
Skip the test on
I know once I empty it, I will be smashing it.
Everything.
And thinking good thoughts about physics.
Wait, a square.
So many good thoughts.
Dude.
No,
that
it's
thing
not
right
the right
there.
answer.
Okay, so let's talk about number 8.
Yeah, let's.
So these both have 2.5 amps. So here's the basic idea, is that you're going to have two basically opposing things happening. So at the top, when the two wires or the two currents are going in the same direction, is that going to cause a repulsion between the two wires or an attraction between them?
Attraction.
Okay? So the top one's going to feel an attraction. What's the bottom one going to feel? Repel. So you're going to have an attractive one, and you're going to have a repulsive one. Right? Which one's going to be stronger?
Drag.
The one that's closer, because there's less distance. Right? Now,
Did you add them or subtract?
because you have two wires, you know force equals mu naught I1 I2 over 2 pi d times that length. Okay? If you ever need that equation on the test, because I know it's not on the equation sheet, I will give that to you. Okay, so don't memorize it. So, basically what you want to do on this one is figure out basically the net force between the repulsion and the attraction.
So how do you?
So on
What is that triangle?
This one's attracting, right? Because they're going the same way. This one would be going this way.
here,
This one would be going this way and opposing.
I1 and
So you would
I2.
do.
No, the
you know
die.
how the length minus
That's
your
times
y?
length.
So it'd be 5 plus the 3 here to do the other one. And then you subtract these.
Yeah, I did.
Okay, so your answer to number 8 on the force would make a not so good GPA, better than your answer to number 7. Still not good. Well, you'd be a rock star at KU. And something times 10 to the minus 6.
Hey, Ryan, I'll start
Fire
you.
bills.
Okay, so on number 8,
Wait,
that force when you get done is something times 10 to the minus 6.
wait, so what for the direction though? Like,
No.
It's either toward the wire or away from the wire.
North and east
would it be
I
toward?
put north.
It's not north, south, east, or west.
Oh,
No,
wait, it's not? It's not north in the plan of paper?
It is.
Why do you say north?
Can you give me
That's
one?
just toward the.
Or,
wire.
you know what, just give me an F on that test too.
Why is it
I'll
up
give
on
it.
plan of the paper?
I know what you're talking about. You took one
Give me
of the You had one of the 0.7 millimeters.
Your answer to number 9 should be close to 100.
Let's go.
Because Darcy, I can't.
You don't have that.
Anything else?
Going once.
Once, going twice.
But it's not 0.7. 0.5.